So this video is going to be a brief review of the complex number system, or also known as the set of complex numbers. But before we talk about the number sets, let's think, what is a set? So a set is a collection of objects, where each object that belongs to the set is referred to as an element of the set. So let's think of some examples of sets and objects. Let's think, how about like a deck of cards? Okay, where each card that belongs to the deck would be an element of the set of the deck of cards. Then we could also think about like sports organizations, like the NFL, NBA, MLB. Okay, so like the NFL, each team you could think of as being an element of the National Football League. And then one that should be familiar to all of you, how about Pinewood School? Where each student would be an element of the set that we think of as Pinewood School. Now, sets often have what we refer to as subsets. So what's a subset, right? It has the word sub in front of set. So a subset is a set consisting of elements that belong to a given set. So before we go over that warning, why don't we think of an example of a subset? And I'm going to go back to our Pinewood School example. Ooh. Okay, so each student is an element of Pinewood School. And we know that there are kind of different ways that we can group students at Pinewood School. Like there's 3 different campuses at Pinewood, right? We have lower campus, middle campus, and upper campus. Okay, so every student that attends lower campus is also a student of Pinewood. So all of the students that attend lower campus or lower campus itself can be thought of as a subset of Pinewood. Same thing with middle campus, same thing with upper campus. And no student attends multiple campuses, so every student that belongs to one of those subsets is also a student at Pinewood, but you don't have those subsets, elements from those subsets crossing over. Like a middle campus student does not also attend upper campus, at least not that I know of. Okay, and then we can go even further looking at subsets for Pinewood School, like how about each grade level? So lower campus has kindergarten, first and second grade, I believe, and then middle campus is 3rd, 4th, 5th, and 6th grade. And then upper campus, well, we're kind of unique at upper campus. We have junior high and high school. Okay, so junior high is made up of 7th and 8th graders, and high school is grades 9, 10, 11, and 12. So junior high can be thought of as a subset of upper campus, but it can also be thought of as a subset of just Pinewood School. Same thing, high school can be thought of as a subset of upper campus, but also just a subset of Pinewood School. The 12th grade is a subset of the high school. 12th grade is also a subset of upper campus. 12th grade is also a subset of Pinewood School. However, the 12th grade is not a subset of lower campus, right? No 12th graders are students at lower campus. Okay, so I hope that kind of clarifies what a set and what a subset is. We're going to now focus on the number set. So we're all of the sets that we're referring to, the elements of those sets are numbers. Okay, and as we enter the number sets, I want to go over this warning that we want to be careful about the terms that we use when we're comparing and describing the size of a set or its subset. And I'll address this multiple times. So we're going to focus on the set of complex numbers and its subsets. Now, looking at this picture, I like this picture and this visual, and I use it every year to give a visual to describe the complex numbers and all of its subsets so that you can see which sets are subsets of other sets. That's a tongue twister. However, this does not do a good job of helping us kind of with comparing size of subsets and sets of the complex number system. Okay, so I just want to kind of repeat that warning here with this picture, and we'll talk about more of why that is in a second, because I think that this picture makes it seem like the irrational numbers look like they're way smaller than let's say the rational numbers, but that's not actually the case. Okay, so let's start with what can be thought of as the simplest subset of the complex numbers, and we'll go from there. So we're going to actually start with the natural numbers. And the natural numbers are also known as the counting numbers. Okay, and I'm going to use the curly brackets to represent my set of natural numbers. So the natural numbers, also known as the counting numbers, are 1, 2, 3, 4, and so on. I'm going to use the ... the ellipsis to show that the counting numbers continue on. Now 1, 2, 3, 4, 5, 6, 7 continue on and on and on to infinity. There are infinitely many natural numbers. You could sit and keep counting the natural numbers forever and ever and ever and ever, and you would never count all of the natural numbers. There are infinitely many elements, infinitely many natural numbers that belong to the set of natural numbers. Okay, the whole numbers. The whole numbers are all of the natural numbers. So the natural numbers, plus 0. So I'm going to use the curly brackets again. So 0, 1, 2, 3. Okay, so all of the natural numbers are actually also whole numbers. So since every element that belongs to the natural numbers is also an element of the set of whole numbers, we can actually say that the natural numbers are a subset of the whole numbers. The whole numbers, however, are not a subset of the natural numbers because the whole numbers include 0, and 0 is not a natural number. Now, here's a great example of where we need to be careful. To us, we would think, okay, well, since the whole numbers include 0 and the natural numbers don't, that must mean that the whole numbers are a larger set than the natural numbers, especially since the natural numbers are a subset of the whole numbers. That's not correct, though. Remember, there are infinitely many natural numbers. There are also infinitely many whole numbers. So there's infinitely many numbers or elements that belong to each of those sets. And there's no such number as infinity plus 1. So just because 0 is included in the whole numbers does not actually make it a larger set than the natural number. So that's kind of crazy to think about, but that's also where I just want to warn you on being careful about the terms that you use when you're comparing the different subsets to each other, sets and subsets to each other. Okay, so let's move on. The integers. The integers are all of the natural numbers. So actually, I should just write, we'll go with the natural numbers plus 0, so all of the whole numbers, but then also the opposites of the natural numbers. I'm going to use the symbol for natural numbers, the fancy N. And by opposite, what I mean is, so like 1, 2, 3, 4 are natural numbers. Their opposites would be -1, -2, -3. So the opposite sign. So I'm going to use the curly brackets again to represent our natural numbers. And I'm going to do that ... actually on both sides of the list. So like -3, -2, -1, 0, 1, 2, 3, ... Curly bracket. Ugh. And that's just to show that the integers continue on towards both infinities. So in both directions, towards negative infinity and towards positive infinity. -2, -3, -4. So those values are getting smaller and smaller and smaller, all the way to negative infinity. And then as we go to towards the positive, so 1, 2, 3, 4, towards positive infinity, those numbers are getting larger. So integers also have infinitely many elements that belong to the integers. There are infinitely many integers. Okay? Since the whole numbers are also integers, the whole numbers are a subset of the integers, which also means that the natural numbers are a subset of the integers. Okay, continuing on, let's look at the rational numbers next. Okay, and the symbol for the rational numbers is that fancy Q. So notice that in the word rational, we have the word ratio, right? And we can represent a ratio as a fraction. So I'm going to write this out. The rational numbers are the set of all numbers that can be expressed as a quotient of integers. Okay, so like as a fraction of integers. Okay, so with the denominator not being equal to 0. So the rational numbers, looking at them, they can all be written as fractions, like in the form a over b. Okay, where a and b are integers. B can't be equal to 0. We're not always going to see rational numbers written as fractions, though. They're numbers that can be written as fractions. So that's also going to include terminating decimals, so decimals that stop, like 0.5, 0.175. Okay, so decimals that stop, as well as non-terminating decimals that have a repeating pattern. So like 0.66666, so 0.6 with the line over it. Use a different color here and I'll put some examples. So don't forget, like, integers, like 7, can be thought of as 7 over 1, right? So all the integers are going to be rational numbers. And then the fractions like 2/3, 0.5, the repeating, non-terminating repeating decimals, so like 0.5, and if I put that line over, that means that the 5 is going to continue repeating forever. Or like 1.237, where let's say the 37 is repeating forever. So I put the line over the 37. Okay, so numbers that can be written as fractions, where the numerator and denominator are integers, terminating decimals, and non-terminating decimals that have a repeating pattern. Those are all rational numbers. The integers, whole numbers, and natural numbers are all subsets of the rational numbers, because all of the integers, whole numbers, and natural numbers are rational numbers. They can be written in the form of A over B. The irrational numbers, okay, the irrational numbers are the set of all numbers that can not be expressed as a quotient of integers. Okay, so all irrational numbers, if you were to put them in decimal form, would be non-terminating, meaning they go on forever. There's infinitely many digits. So non-terminating and non-repeating decimals. And the non-repeating part, what I mean by that is that there's no repeating pattern. So numbers can repeat themselves. It's just there's no way to memorize the entire number, because there's no repeat, there's no sort of pattern, and there's infinitely many digits. Now, some famous irrational numbers are the transcendental numbers. And we'll talk more about what transcendental numbers are once we get to chapter 2 in pre-calc honors, and we talk about polynomials and their roots. But the transcendental numbers. And the most famous transcendental numbers are E, Euler's number, which is approximately 2.71, and then pi, 3.14 approximately. Okay, and then also non-terminating, non-repeating decimals, so like 3.521, and then if I put that ... it just means that the digits continue on. There's no repeating pattern, so I don't have that line over. There's no way for me to guess what number would come next. If we were to put like the square root of 2 in decimal form, there would be no repeating pattern to the square root of 2. The square root of any prime number, basically the square root of any number that is not a perfect square. So like the square root of 5, the square root of 14, okay, are all, square root of 14 are all examples of irrational numbers. Now the real numbers, you guys have been working within the real numbers system for a very long time. So the real numbers, the set of real numbers, are made up of the rational numbers as well as the irrational numbers. So like 0 is a real number. E and pi are real numbers. Negative 17 is a real number. 1.589 repeating is a real number. 7/6 is a real number. Okay. So all the rational numbers and the irrational numbers. So the rational numbers are a subset of the real numbers. The irrational numbers are a subset of the real numbers. Now, the rational numbers had a bunch of subsets as well, right? We talked about the integers, whole numbers, and natural numbers being subsets of the rational numbers. The irrational numbers are not a subset of the rational numbers, and the rational numbers are not a subset of the irrational numbers. So a number is either rational or it's irrational, but it's not both. So they are not subsets of each other. However, the rational numbers are a subset of the real numbers. The irrational numbers are a subset of the real numbers. And those two subsets together make up the set of real numbers. Okay, so now the imaginary numbers. Okay, so imaginary numbers can be written in the form a plus bi, where b is not equal to 0. I just want to remind you that I is actually equal to the square root of -1. So remember, the square root of a negative number is an imaginary number, and the square root of -1 is equal to I. So if a number has an I in it, an imaginary part, then it is an imaginary number. So some examples could be like 1 plus I, or 7 minus root 2I. How about like pi plus EI, even 2I, or even I just by itself. Those are examples of imaginary numbers. So no real number is an imaginary number. The real numbers are not a subset of the imaginary numbers. If there is an I in a number, then it is an imaginary number and not a real number. However, a subset of the imaginary numbers, we could say, are the pure imaginary numbers. So those that are in the form of bi, so where a is equal to 0. So like I would be a pure imaginary number, 2I, EI, okay, pi I, and so on. Those are pure imaginary numbers, and the pure imaginary numbers can be thought of as a subset of the imaginary numbers. So when we put the set of real numbers and the set of imaginary numbers together, we get, the set of complex numbers. So all complex numbers can actually be written in the form of a plus bi. It's just the real numbers have b equal to 0, whereas the imaginary numbers do not have b equal to 0. B is not equal to 0. So the real numbers are a subset of the complex numbers. The imaginary numbers are a subset of the complex numbers. And then those two sets together, when they're combined, make up the complex numbers, or the set of complex numbers, the complex number system. Again, there are infinitely many elements, infinitely many numbers that belong to each set that we just talked about. So while this picture makes it look like there are different sizes of subsets of the complex numbers, each set has infinitely many elements that belong to it. There are infinitely many pure imaginary numbers, infinitely many imaginary numbers, when we're talking, you need to really think about the definition of what a